Okay, so here's what's happening today. We're going to start off with a little bit of a Kahoot, and then we're going to go into piping, shells, and drums. A little bit of it's the next topic after tubes. A reminder that we've got a quiz this weekend. It's on combustions, fuels, flue gas analysis, the type of stuff that was in that particular chapter. And I guess that there is some overlap to what you're doing in therm as well. So if it's in that chapter, it's fair game for the quiz. Starts tomorrow morning, 8-ish, goes until Sunday evening. This is Thanksgiving weekend. So we don't have a class on Monday. Enjoy your long weekend. And Joe wants me to extend the quiz. Who wants to extend the quiz until it goes until Monday night? Four people. Okay. Everybody wants. Okay, so I'm going to do that. I'm going to extend the quiz, and it'll go until Monday at 11:30, something like that. Anyway, enjoy your Thanksgiving. I'll see half you anyway tomorrow for labs. So now my mouse only wants to stay as a pointer. Okay, so here's our yesterday's question. I left you at the end of the class. I left you with the following question, something like, we got a tube that's strength welded into place, not an expanded tube. It's made of SA192. That's something that we can find on ASME 2D, even the little mini one that I gave you. And it said that the mean wall temperature was 300 degrees Celsius. That tube had an outside diameter of 50 millimeters, and it needed to have a maximum level working pressure of 1.75 megapascals. And the question was, what's the minimum thickness? So if we go to PG 27.1, that is the tubing formula. And okay, so this is the tubing formula, PG 27.2.1. And it's used for tubes, downcomers, but it has to have internal pressure, so we can't use this for fire tubes or furnace tubes. And basically anything that is 125 millimeters in outside diameter and less. So if we were talking about a tube, say a very large external downcomer for a large utility type of boiler, that would immediately kick into the next formula for larger stuff. So in order to determine the minimum thickness, we need to know P, which was 1.75 megapascals. It was given. We have the outside diameter, which was 50 millimeters, which was given. We need to know S, and S, if you looked it up, for SA192 at 300 degrees Celsius, you got 91.9. Why did it do that? My screen suddenly zoomed in, and I'm not too sure why. That's okay. Okay, so W was a strength reduction factor for welded materials. And what we remember was that anything that was 427 degrees Celsius, it doesn't matter what type of material it was, anything 427 Celsius and less had a value of 1. So we can actually kind of skip that W, but we are making a list of the things that we put into the formula. So we do need to know what W is. We need to research it. The diameter is 50 millimeters, and E, if you recall, was a factor for expanded tubes. This particular one is not expanded, so it's 0. Now these are the units that we use. For S, we're always using megapascals. For P, we're always using megapascals. For diameters, or radii, depends what the formula is. We're always using millimeters, and additional thickness is in millimeters. So then it's kind of like plug and play. And you should have come up with 0.722 millimeters, let's say 0.72 millimeters. That's a minimum thickness. The tube can be thicker than that, but it can't be thinner than that. Now, is that okay? Because somewhere we were looking and said that we needed to have a minimum thickness of 6 millimeters. So can we actually use a material that's like 3/4 of a millimeter thick? Is that okay?
No.
It's not okay. So are you suggesting that that tube has to be at least 6 millimeters thick?
Yeah.
Okay. This is the common misconception. The 6 millimeters only applies to plate. And this stuff isn't plate. This is tube. Okay, remember we looked at product forms.
Oh.
So tube, yes, and pipe, yes, can be less than 6 millimeters thick. And the only time we're worried about pipe being at least 6 millimeters thick if we've got a great big pipe that we're using for a shell. So if I make this stuff, if I order this material as 3/4 of a millimeter thick, that's a-okay. All right. Okay. Easy to get stuck on that. 6 millimeters refers to plate, and plate is used for making shells. Plate is used for making tube sheets. Plate is used for making heads, so flat heads, formed heads that are hemispherical or ellipsoidal or something like that.
So,
Okay.
and Dave, this material would be okay for making what exactly? Anything outside of that?
Tubes. Tubes.
Okay.
And if you take a look at ASME 2D, when you look up that material, SA192, the product form says tube. You can't buy SA192 plate. It doesn't exist. SA192 is, by its very definition, it's a tube. All right. Any other questions? Okay. Then here we're going to do a Kahoot. Get your Kahoots ready. Go like this. Gotta go like this.
Do you need an account for this one, Dave?
No, I don't think so. You just phone
Okay.
or an Android device or an Apple. Oh, look at that. Cool. Okay, do you see the Kahoot on your screen right now?
I see on your screen, on this screen here, yeah? Sharing your screen.
Okay. All right. This is a review of what we're doing yesterday. And there's your game pin. Okay, I'm gonna lock it in about a minute. Last chance. Okay, here we go. Oh boy, that was a tough one, wasn't it? Let's take a look at this vessel here. I'm going to, I wish I could draw on this right now, but I can't, but I'm just going to use my pointer. Can you see my cursor?
Yeah, we can see it.
Okay, excellent. So this here, okay, so you can't actually see the longitudinal joint. You know, you can see right up here. Okay, a longitudinal joint goes from one end to the other, and the longitudinal joint gets what's called circumferential stress. So what the question was about was what's greater, the circumferential stress, which is creating circumferentially, trying to rip apart the longitudinal joint, or the longitudinal stress, which is in the longitudinal direction. And mathematically, the circumferential stress is about double that of the longitudinal stress. So let's go back to this. So the question was the longitudinal stress is about 2 times the circumferential stress. No, it's the other way around. The circumferential stress is about 2 times the longitudinal stress. Okay, that was a tricky one. It was tough. Okay, next question. Okay, so there were 3 correct answers for that one. And if we take a look at this thing here and think about the formula that we just used, what were the factors? There was the material strength. We had to look up a temperature. There was the diameter of the vessel, which is one of the factors in it, and the thickness of the material. So those are the 3 main factors. And this particular image shows length. And when we were going over the actual formula and you know putting the stress and pressure formulas together, we saw that it was independent of the length of the vessel, so that L appeared in the numerator and denominator, and it just canceled out. Okay. So what you're taking a look at here is actually A53 grade B pipe. It says A53 grade B. And now SA53 grade SB, the S stands for seamless. Now we could have grade FB and we could have grade EB. Grade EB, it would be manufactured through an electric resistance welding process. Okay, but it doesn't have the E. If it said FB, it would be furnace butt welded pipe. But this is SB, which means that it's seamless grade B. Tricky ones, hey? But this is stuff that we looked at 2 days ago. Well, congratulations, those who got that right. This is another tricky one. So if you recall, SA285 grade C is a particular grade of boilerplate. A means that it is a ferrous material. The letter S means that it is a ferrous material that is approved by the American Society of Mechanical Engineers for boiler and pressure vessel construction. The material is known as A285. It's the same thing. The S just means that ASME has put their stamp of approval on it. Okay, that's all that the S means. So, in the previous question, the question was about SA53 grade B pipe, and that picture, and the picture did not say SA53. It said A53. So, let's say, for example, you're ordering pipe for your plant, and you want SA53 grade SB pipe. Then you would not order SA53 because you're going to confuse people. They don't know what it is you're ordering, but you will order A53. And similarly, when we order boilerplate, if you're in a boiler manufacturing shop or pressure vessel manufacturing shop, you wouldn't order SA285 grade C. You would order A285 grade C. It's the same stuff. All right, 6 millimeters thick. Now, a close one is millimeters thick because it does say in part PG16 that if you're going to attach a stay bolt, it has to be at least 8 millimeters thick. So that's where the 8 millimeters comes in. Now, take a look at that. That's it's a formed head. I think it looks to me like it's an ellipsoidal head. It hasn't been mounted onto a boiler or pressure vessel yet. And that's plate. Yeah, it doesn't look like it's flat plate, but it started off as flat plate, and there's an example of something that has to be at least 6 millimeters thick. Right on. So So that, in fact, is PG 27.2.1. Those are the two formulae in there. One is solved for thickness, the other one is solved for maximum working pressure. This is the one that we just did with the tubes. And so if a tube exceeds 125 millimeters, it kicks us out into the piping and shell formula. Yep, 1. Okay, and that was the same in the little practice I gave you yesterday, and we looked at table P26, and like, oh no, we have to find some value for 1, and I gave you a little shortcut. I said, look, 427 degrees Celsius for all the materials. Less than that, W is equal to 1, or unity. So we didn't actually have to put it into the formula, but we had to demonstrate that we researched and found, in fact, that that particular material at that temperature that it operates at, if it's 427 or less, that the W is 1. Yes, ASME code 2D, that's where we find that stuff. As a matter of fact, what we're going to look at is this thing here called Table 1A, and this is that table that spans 4 pages. We find the line number, we find the material, actually we find the material, then we find the line number, and we follow that line number across 4 pages, and we find the allowable stress at whatever the temperature is. Oh, Gazator the Burninator is burning up the village. Yes, so that's why the blacksmith has that poker red hot so that he can form it into whatever shape with a compressed force relatively easily. And so how this works the boilers is the hotter the component, the weaker that it gets, and we see that with ASME 2D. So that's why we need to know the stress or strength at temperature. That's correct, because recall that that little letter E there is about additional thickness required for tubes that are expanded into place. These tubes, according to the question here, they're strength welded. If they're strength welded, we don't need any additional thickness. In that case, E would be 0. Now, the interesting thing is E can only be 0 or 1. Okay, so based upon the diameter of the tube and the calculated thickness, make a decision. Do we have to add an additional millimeter, or do we not have to add the additional millimeter? So here we go. The winner. Congratulations, Gazator, the Burninator. So, there we go. Okay, so next we move on. And have to open up our ASME code section 1. So where do I have that file? Open recent. ASME. Where are you? Okay. I'm going to have to find it then. Okay. There you are. Can you see my mini BPVC section 1, part
Yep.
PG? All right. So we left off, we took that tubing formula, and now we're going to go to the piping drums shells formula, which is right here, PG 7.2.2. Again, all we've done is we've modified the basic formula that we came up with. So we actually have 4 formulae here. The first one we have is thickness, but this is thickness expressed in either terms of outside diameter or in terms of inside radius. So it really depends what the question is given you. Maybe the question is giving you an inside diameter, and it says, what's the thickness? You go, oh, gee, how am I supposed to know based upon the inside diameter? I need to know the outside diameter. Well, if they give you the inside diameter, you can use the inside radius formula, okay? So let's take a look at some of the other things here. We know what S is. We know what P is. We know what D is. Now we know what R is. And again, all of the symbols are here, PG 27.3. Okay, so if you ever get a little bit confused exactly what these things are, you can find them. So we need to find out this capital letter E. The capital letter E is not the same as the little letter e over there. So what is capital letter E? E is efficiency. Oh, okay. And then it says PG 27.4.1. Guess what? That's actually one of our notes here, PG 27.4.1. Okay, so that's efficiency. The next thing is this small letter Y. Well, what the heck is Y? I go through here and I find Y, and Y is a temperature coefficient that says PG 27.4.6. Wow, 27.4.6. Well, they don't have it listed here, but we'll go there anyway. And then the capital letter C, what the, oh, it's right there. Minimum allowance for threading and structural stability, C7.4.3. Okay, 27.4.3 is one of the things on our list. So let's first of all go to PG 27.4.1. I think that link isn't going to work. No. PG 27.4.1. So it says, what is E? E is efficiency. and E is 1, that means 100%. Okay? Whenever you see an efficiency represented as 1 or unity, that means it's 100% efficiency. So take some notes right now. Get your pencil out. What is meant by efficiency is they compare the strength of the parent material to the strength of the joint. So what we have is a longitudinal joint, and it's a weld joint. And that longitudinal weld joint, if the weld joint is every bit as strong as the parent material, it gets a of 1. If, though, we determine that the weld joint is weaker than the parent material, then we have to claim some efficiency less than 1. Does that make sense? You can hear
Yes.
me okay, right? Okay, excellent. Okay, so E is 100% efficient, or 1, for seamless cylinders. Oh, well, that makes sense. So I got a cylinder that doesn't have a weld joint. It's seamless. Perfect. So I'll give it an efficiency of 1. Oh, but without openings, space to form ligaments. I think what that means is we have to talk a little about what ligaments are. E is the ligament efficiency that we don't calculate in third class, but you'll do it in second class. And W is our friend, the weld joint strength reduction factor from PG 26. And we know that anything 427 degrees or less gets an efficiency of 1 because the weld joint strength reduction factor is 1. And we also know that for plain carbon steel, it's always 1. So E is going to be 1, or it's going to be some number less than 1. So let's very briefly talk about ligaments, exactly what is meant by these ligament thingies, okay? So we are going to do sawing, and here's a steam drum. Or, I'm going to make it a mud drum because it'd be easier for me to show. I got and I've got a whole bunch of tubes attached to the top of it. So what I have is a regular pattern of holes. And what I have done then is, along that plane, I've got less material to oppose the circumferential stress. So here's my circumferential stress. And the cross-section of material is much less because sort of if I was to look at it from the side, like if I was to cut through it, I'd see a tube hole here. I see another tube hole there. Another tube hole there. And you get the idea. So instead of having full material thickness, which would give me 100% efficiency, maybe after I've drilled all the holes, I've only got 50% of the material remaining. Well, ASME always tells us to use the weakest part. So let's say that this is the longitudinal joint. The longitudinal joint is 100% efficient. It's welded. We've done volumetric testing in the form of X-ray, or maybe we've done volumetric testing in the form of ultrasonic testing. Okay, it's 100% examined, and so we say that that joint is 100%. We go, wow, what an awesome weld. Perfect. But now we got all these holes over here. By design, we want those holes to be there because we've got to attach the tube somewhere. And now the weakest part is this plane here, which we said is only, in the case, 50% efficient. In that case, E is going to be the lesser of this efficiency and that efficiency, so obviously 0.5. Okay? We good?
Yep.
All right. So let's go back here. So E is for seamless cylinders without openings, space to form ligaments. And a ligament, I should say, is the actual material that was in between. Okay, what are you doing here? It's not drawing for me. Anyway, the ligament refers to the material that left over in between the tubes. Okay, those are what ligaments are. So if I do have ligaments, then what I do is I put the ligament efficiency in. And then these two things, PG and PG53, that just tells you how to calculate ligament efficiency. All right, so that's E. Next thing is we've got this small letter Y, and Y is temperature coefficient under PG 27.4.6. So let's go to 4.6. Here it is. Y is a coefficient having values as followed. Here's the dealio with Y. Y is only about stuff at high temperature. So what we find...
else, Dave, but I can't see your screen right now. It's just white.
Can anybody else not see my screen? Can people see my screen, yes or no?
I just see
no,
white.
it's white.
It's white. Okay, let's try this again. Thanks for letting me know, because like I said, I can't necessarily see what you're seeing when I'm doing this.
Yeah, it was good up until just a few seconds ago. You can see it now, yep.
Okay, now can you see the boiler pressure vessel code?
Yeah, we can see the chart there that you're looking at.
The table. Excellent. Thank you. I so appreciate when you guys let me know this. So, okay, so this it's the temperature coefficient. That's all it is. And what they're saying is, if you're operating above 480 degrees, you have to know, is it a ferritic steel? Is it an austenitic steel? Is it some alloy steel? And so look at these temperatures, 510 Celsius, 540 Celsius, 565 Celsius. Almost anything that you are going to be doing in third class, 480 degrees Celsius and below. So take a look at the number. Is it ferritic steel? Is it austenitic steel? Is it an alloy? Is it this, that? Is it whatever? It seems to always be 0.4. So you'd be really hard pressed to have to use a number other than 0.4. But just so you're aware, that's where you look, and you have probably 0.4 is the value for Y. Then the last thing is this letter C. And so let's find C. C is additional thickness.
So where would you find something, Dave, that's over 480 degrees? Wouldn't you find that like inside the furnace somewhere? Water tubes or something? Wouldn't that be?
Remember that we're talking about mean wall temperature. Okay, so if it's a tube that is absorbing heat in the furnace, you take a look at the mean wall temperature. So you'd have saturation temperature on one side, you'd have furnace temperature on the other side, and then you would determine the mean temperature. So you might be over 480 in that situation. But if you think of, say, a downcomer or a tube that is in the convection section of the boiler, you're going to have a much, much lower temperature. Superheaters for sure would be at a higher temperature. But what I'm trying to do is limit our discussion really to what you learn at the third class level. As you go on to second class and first class, it becomes increasingly complex. So you just need to have the foundation, that's all. Okay?
Sounds good.
Excellent question. Okay, so C is additional thickness. Okay, why additional thickness? Maybe because you're anticipating corrosion and erosion. FYI, though, they build it into ASME code section 1, boiler manufacturers 99.9% of the time do not put in a corrosion factor or an erosion factor. If they did, that would be C. So, but where we do find C is when we pipe. Okay, so with pipe, we are going to use a particular value C. If we've got an NPS 3/4 pipe equal to or less than that, we use 1.65 millimeters. If we've got a pipe that is greater than 3/4 of an inch, we use the depth of thread. You go, oh, how do you figure out the depth of the thread? Well, you look at note 3, and note 3 is here, and it says, this is the formula, H is equal to 20 over N, where N is the number of threads per inch, or number of threads per 25 millimeters. But you don't really have to worry about it, because it's here in this table. So, most pipe has 8 threads per inch, so H then is 2.5, which then becomes the value of C. Now, once you get to, I can't remember what NPS size, you get to 11.5. I can't remember what NPS size you end up with 11.5 threads per inch. But at a particular pipe size, you get to 11.5 threads per inch, and with 11.5 threads per inch, C is 1.77. This used to be really, really complicated. ASME has really simplified this. So let's put it this way. Number 1, C is corrosions. And if the question doesn't say corrosion allowance, C is equal to 0. The next thing is, C is additional thickness for structural stability. So maybe you've got a thin wall pipe and you know, you want to, as a designer, add a little bit of extra structural stability. But the most important thing is where you are putting threads in, because when you're threading, you're actually some of the pipe material, so you have to compensate for having removed material. So let's see what that looks like. And again, it's not going to let me.
The screen is white again, Dave.
Yeah, it's supposed to be white now. Okay, so I'm drawing a pipe. Can you see the pipe? Can you see the pipe that I'm drawing?
Yes, we can.
Yep.
Perfect. Okay, so it's supposed to be that thick, but now what I'm going to do is I'm going to put a whole bunch of threads in it. And, you know, it's NPT thread, which is National Tapered Pipe Thread. So what we end up doing is we remove that much material and we make it actually thinner. That then is H, the depth thread. And so in some situations, H is 1.77 millimeters. That's if you've got 11.5 thread per inch. Or H could be, what was the other one, 2 point something? Let me just see here. 2.5. 2.5 millimeters. If you've got 8 threads per inch. How do you find the inch? One good place is Engineer's Toolbox. The good thing about this is I'm not certain that ABSA is going to give you anything like this. Okay. So now we know what C is. We know what P is. We know D is. And we know what Y is. we know what E is. So let's give you guys a question to work on here. Let me just find something here. Okay, we're going to do a shell. So let's say I've got a shell. It's a fire tube boiler shell and has a 2750 millimeter outside diameter. So in other words, 2 and 3, almost 3 meters in diameter, okay? It carries saturated water and steam. It's SA 285, grade C, and it's got a MOP is 2070 kPa, and the mean temperature is not to exceed 250 degrees Celsius. So what that probably is the saturation temperature of the water plus a few degrees. The joint is welded and all joints have an efficiency of 1. And it says, what's the minimum thickness? So I can go back to my formula. I have to go to PG 27.2.2, and I'm going to use a minimum thickness formula that that uses outside diameter, because the outside diameter is given to us, so I don't need to use the inside radius formula. So D over 2SE plus 2YP plus C. So let's write that down here. Thickness is equal to pressure times diameter over 2SE plus 2YP plus C. Now the question doesn't say anything about a corrosion allowance. It doesn't talk about threading. It's not a threaded shell. So whenever we got a drum or a shell or a header, C is almost always 0, unless the question says add an extra 2 millimeters of additional thickness. So look, I'm plugging in some numbers here. So the pressure is given to us in kilopascals. We got an issue here because the unit we always use for pressure and stress is megapascals. So 2.07 megapascals times the shell diameter, which has to be in millimeters. Over 2 times, allowable stress. Can somebody please look that up in ASME 2D and see if you can find that? I hear a bloop. Oh, that was my email blooping. And E1, we'll put that in there. I'm just going to leave a bloop for S. So as soon as somebody finds the value of S from table 1, plus I also need to know, somebody, I need you to look up the value for Y. What is the value of Y for this particular material?
Y is going to be 0.4.
That's correct. Yeah, because it's fairly low temperature.
Where was the S value again, Dave? That was in the other document, right?
S will be an ASME 2D. At 250 degrees Celsius.
I got 108 here.
Okay, that sounds good. So go ahead and spit out a number for me.
How did you get 108, Andrew? I'm getting 88.9.
Make sure you're looking at the right line.
1 second, I'll check again. I just closed it. You're looking at a grade A, Brett. It's grade
Yeah,
C.
which line were you following? Which is grade C?
It'll be number 3 on the next table.
Yeah, that sounds right. Line 3 sounds about right.
Yeah, gotcha.
Is it 108?
It is, yep.
Yeah, that sounds right to me because grade C is pretty strong stuff. Who's got an answer then? Scream out the answer when you get.
I got 26.34.
26.34.
I could be wrong though. I did it kind of quick.
I got 26.15.
Okay, that's what it is. It's 26.15. Yeah, so Speedy there, you probably punched in a number a little bit wrong or something like that. There you go. So here's what I'm going to do is I'm going to give you a little homework assignment. All of the sheets are uploaded into that news area, and stay tuned for the news. And in about 5 minutes, I'm going to post some of the questions that I want you to do as practice. Some of them are tubing, and some of them are shell questions. Thanks for sticking around a little bit longer, folks. I know you got to run to another class now, so have yourselves a great day, and we'll see you tomorrow morning.
See you tomorrow.
Thank you.
Bye.